So kinematics describes how things move, but it does not explain why things move. But still, I'm going to tell you a little bit about how things fall near the surface of the Earth, and we're not going to get into why. We'll get into why next week, but just to make sure you can do whatever homework you need to do, I want to tell you a little bit about how things fall. So let's say near the surface of the Earth. I think we can all be sure that's true for all the students. Near the surface of the Earth. Now we're going to go over a few cases of motion. Let's see, one is that all objects fall down with acceleration A equals 9.8 meters per second squared. So the experiment we're talking about here is the case where you just have a mass, some object, and it's falling that way down. So I'll put an A there. Okay, this is usually true. Let's check it. Here we go. It did fall, and there goes my chalk. The one thing we got to put though is assuming you can ignore air resistance. Can ignore air resistance. Again, we'll get into it next week when we talk about forces, but for now you'll usually see this written in a problem, and they just want you to use the acceleration, and of course the cause of this is gravity. Okay, we'll get into it next week. But what's interesting is all objects fall at this rate, at this acceleration, no matter what their mass is, if you can ignore air resistance. So what I want to do now is go test that. So let's go test that out in the quad. Welcome to the Engineering Quad at Rice University, home of 45, 90, and 180. We're going to drop Hal off of 45 to demonstrate that all objects fall at 9.8 meters per second squared, assuming you can ignore air resistance, and also for that thing that happened that one time, Hal, remember? We're also going to drop a second mass. Meet Al. Al is an aluminum sphere, also 76.2 millimeters in diameter, but a lot lighter, because aluminum has about a third the density of steel. So while Hal is about 1.8 kilograms, Al is only 0.6 kilograms. And we'll see if they fall at the same acceleration. Let's see what happens. Here we are, perched atop 45, ready to do our drop. Now, one tip I want to give you, if you ever have to tell aluminum from steel, there's a few different ways. One way is that aluminum weighs less. We already talked about that. The second is the look. So aluminum tends to be kind of a brighter look. Steel's kind of darker blue. The third way is the taste. If you lick aluminum, it doesn't taste like much. It has a nice oxide layer to it. If you lick steel, it's got kind of a metallic taste. You taste a little bit of machine oil in there. So enough metallurgy. Let's go ahead and do our drop. So here we go. We're going to hold them at the same height, release them at the same time, and watch the acceleration. Oof, that was fun. Oh, he's got a few grass stains there. Get those off. And now we're going to talk a little bit more about acceleration near the surface of the Earth. Another case you might encounter is that objects move down an inclined plane, and by that I mean something set up like this, and it has some angle theta, and it's either a mass sliding or a ball rolling down the plane. If a ball goes down that plane, the acceleration looks like this. A equals that same number, 9.8 meters per second squared, the free fall acceleration times sine theta. All right? So you can see what's happening here is it's reducing the acceleration. You can imagine if you turn this all the way normal, you wouldn't even really be rolling or sliding down the plane at all. You'd just be falling. If you turned it all the way, theta would be 90 degrees, the sine of 90 degrees is 1. You get 9.8. If you have it just with a slight angle, theta is very small, sine of a very small angle is a very small number, so you get a very small acceleration. Okay, so an inclined plane is a way to sort of tune down the free fall acceleration and to get a value more like what you want. Of course, this is assuming you can ignore friction, and I've written myself into a corner, and rolling. Oops. Just like we had a little thing to think about for free fall, assuming you can ignore air resistance, you'll only get this acceleration if you have a frictionless object sliding or you have something rolling and you ignore the effects of rolling that we'll be talking about later. So this is sort of what we've been doing with our inclined plane, is we were having Howell roll down it and the acceleration wasn't quite so ridiculously high because we have it at a very small angle. So that tuned or lowered the acceleration. And an experiment like this really is how Galileo first observed the constant accelerations that you find near the surface of the Earth. Because so Galileo observed constant A. And he did it with something like this. We've propped it up and we've put these little clips on the track at a certain spacing. And the way you can sort of confirm that you have a constant acceleration without a bunch of accelerometers and position sensors and all this modern equipment is you can think about the equation that the position is 1/2 acceleration times time squared. And since this happens in time, you can listen or watch for something to happen at uniform differences in time. So you could say, I want to hear a click, I want it to pass a wire, whatever it's going to be, at t equals 1, 2, 3, 4, 5, etc. And then you just have to ask yourself, where do we need those things to happen? Where along the track should they happen? So you could say, well, here's x. Well, you just plug in t. So it's 1/2 a and then times 1 squared. All right? And then 2, would happen at 1/2 a times 2 squared, so that's 4. And 3 would happen at 1/2 a times 3 squared, that's 9. 4, 1/2 a, 16, 1/2 a, 25. So you can see from this equation, if you want things to happen uniformly in time, then you need them to be separated. If it's accelerating, they need to be separated by something that's increasing as the square of the time, right? So we got 1, 4, 9, 16, 25. So that's how Galileo did it, something kind of like this. So here we've put these little clips, and sort of the units, the absolute values don't really matter. I just, a could be some number, 1/2 could be some number, as long as the relative spacing of the clips follows that ratio, you're fine. So here I put them at 2, and then 4 squared, 8, and then 18, and then let's see, 16 times 2 is 32, 25 times 2 is 50, etc., going all the way down. So what we're going to do is roll, or let Hal move, not roll, move down with some acceleration, and we'll see if the sound is uniform, if the clicks are uniform. So here we go. We're going to hold it right here and let it go. Sounded pretty good. So you could hear those, and we amplified them a little bit in the video, so you could hear those uniform clicks. So even though the spacing wasn't uniform, the clicks in time were uniform. And according to that equation, that's how you can confirm that acceleration really is constant. Now, those little clicks in this big amphitheater full of 200 students, 250 students eager to learn physics aren't quite enough. So we have something a little bit more dramatic that we do in the real class, and I want to show that to you. Let's see, so I tie this on here. All right, so now we're going to do this experiment again. But now, rather than use the inclined plane, we're going to let our masses fall at the full 9.8 meters per second squared. And again, in this case, since their spacing is in relative amounts of 1, 4, 9, 16, 25, you should hear them hit the ground or hit this plate at constant intervals of time. But it'll be louder and longer and faster and more exciting. So here we go. Let's go. So those are on a clip up there, and when I pull the clip against the ceiling, that's what releases the balls. There you go. So hopefully you could see and hear that they hit the plate in uniform spaces of time, which means they fell at a constant acceleration.